Welcome to our video on parallel algorithms for universal compression. This is joint work by Nikhil, Krishnan, and I. The motivation for our work is really big data systems. In these systems, we have bottlenecks including data storage and data transfer. And we'd like to use compression to help us reduce the data storage and transfer requirements. A key question is whether parallelization can help us compress well. Some background. Universal compression methods can adapt to unknown input statistics. Now, when you consider serial compression methods, which are not parallel, the best serial universal compressors have already achieved the best possible compression quality. At the same time, existing parallel algorithms have either high computational complexity and/or they don't really compress very well. As an example, we'll see soon that naive parallelization doesn't compress well. Consequently, we had two goals in this work. First of all, we wanted to develop fast algorithms that compress lengthened data in order n over b time when the degree of parallelization was b. Secondly, we wanted our compression quality to be almost as good as the best serial methods. To do so, we use a context tree source where the last several bits, which are called the context, allow us to select a state of the tree, and that state has a conditional probability for generating the next bit. As an example, if the last bit, the context, was a 0, then we begin at the root node, we follow the label 0, and we reach the state which is, again, labeled 0, and that state has a probability 0.8 for the next bit being equal to a 1. This type of source is more flexible than the Bernoulli source where all the input bits are independent. And additionally, in comparison to a Markovian source, which is a full tree, in this case, the context tree source is pruned and often contains far fewer states. That's very efficient for compression. We'd also like to consider universal compression, which is the case where the input statistics are unavailable. Now, hypothetically, if they were available, if the source was known, then the entropy rate denoted by h is the number of bits per input symbol on average. That's the fundamental lower bound on compression quality. Now, of course, in practice, the source is often unknown, and we need to estimate the source model, and in our case, the tree structure and the conditional probabilities corresponding to the leaves. The redundancy rho of x is the excess coding length beyond the entropy. So L of x is the coding length in practice of the universal compressor, and n times h is the average entropy. Resonance bound tells us that rho of x is lower bounded by roughly half log n bits per unknown parameter. Now, that might not sound much, but in practice, the number of states in the tree is very large, and consequently half log n bits per parameter is quite a bit. The technique that we use for universal compression is a two-pass minimum description length technique, where we have data, and then we perform tree pruning to give us the best tree source S star, and then that best possible source is used by an encoder that looks at the data, the input x, to compress it, and finally what we encode is the structure of the best source and the compressed data. Now, it so happens that this two-pass MDL approach has low redundancy. I mentioned earlier that naive parallelization doesn't compress so well, and let's understand why. If we begin with data and we partition it into B blocks, and then each of those blocks is compressed independently, what'll happen is that the universal compressor will find the best optimal source for that block, and then it'll compress the block using that source. Each of these blocks is going to have a length of n over b. Consequently, the redundancy is going to be lower bounded by order of log n over b bits. And because we have b of these blocks in total, the aggregate redundancy is on the order of b log n over b. This is a lot more than the redundancy in resonance bound, and we'd like to do better. We can do better using a parallel two-pass MDL encoder. As before, we partition the input into blocks. We have blocks coming into different parallel units. The parallel units accumulate statistics about their blocks. They relay those statistics to the coordinating unit, which estimates the optimal source as before. After that, the optimal source is used to compress the B blocks in parallel, and finally we encode the compressed blocks and the structure of the source. The PTP-MDL decoder receives the structure of the optimal source and all of the compressed blocks. After demultiplexing them, it sends to each of the parallel units the structure of the source and the corresponding compressed block, and that processor can decompress that block. Now that we have all the decompressed blocks, we have the original input. Let's take a look at the data redundancy of this parallel two-pass minimum description length approach. Our first result is that the worst case redundancy of this PTP-MDL algorithm over the maximum likelihood entropy is bounded by the following term, where n is the data length, b are the number of blocks or the degree of parallelization, and s is the tree source. Now, what you can see that we indeed have s over 2 log n, which is basically resonance bound, and we also have another term of pretty much b log n over b. And that other term is typically quite small because the degree of parallelization is often much, much smaller than the number of states. Because of that, this approach compresses almost as well as the best serial methods. Now, in terms of time complexity, our second result is that PTP-MDL compresses and decompresses in time order n over b. Moreover, PTP-MDL is implementable on FPGAs, GPUs, and other distributed architectures. Another advantage is that if you think about it, any part of the compressed file can be decompressed without decompressing the entire file, because you have that compressed block. And there are applications to random access decompression, such as in data server applications and image decompression. Next, we'll look at some numerical results. The first numerical result will show us on the horizontal axis the throughput in megabits per second of several different compression schemes, and the vertical axis will be the compression ratio in bits per byte. So really, we want to move toward the right and we want to move down. And what we see in the dashed line is the efficient frontier, which are the algorithms that are closest to the bottom right-hand corner. And if you look at PTP-MDL, which is shown in asterisks, these asterisks for 1, 10, 100, and 1,000 blocks get closer and closer to the efficient frontier. And what I'm really saying is that if you have a large degree of parallelization, you're going to have a really nice trade-off between compression quality and speed. The next numerical result involves the compression ratio as a function of the number of blocks. Here, the number of blocks appears in the horizontal axis. The vertical axis shows the compression ratio as before. And we can see that when we have more blocks, the compression ratio goes up, meaning that we don't compress quite as well. At the same time, we can see that some files, like the E. coli file, which has a pretty small tree source, doesn't really suffer that much from more blocks, while text files, such as the Bible file and the World 192 file, the degradation and compression ratio is more severe. Our next and final numerical result involves again on the horizontal axis the number of blocks, and the vertical axis now shows the compression throughput. The bottom line from this plot, which is on a logarithmic scale, is that there's a linear speedup in the number of blocks. So let's summarize. We've seen that the MDL approach using context trees scales well with more parallel units. We also have that neat random access property that allows us to decompress in a selective way. Now, I'd like to note that we've really implemented this in C++ in a prototype manner with a serial algorithm, a serial compressor and decompressor, and that has allowed us to predict the performance of a full-scale parallel implementation, which we haven't really performed yet. Additionally, there's some potential to improve the compression quality using different quantization approaches, because really the way how we're encoding the conditional probabilities is using quantization. Finally, I'd like to thank you for your attention. Here are some links to our personal web pages, publications related to this work, and acknowledgments. Thanks a lot.